Hello, this is Dylan Blair, and in this lecture slide we are going to go over Chapter 9 examples. And Chapter 9, as a reminder, this is basically just the broad study of vectors. Okay, so let's get started. Let's assume that we have two vectors defined. Say we have vector v is equal to, let's say, 2 comma -3, and let's say we have vector w is equal to, let's say -1 comma -1. Okay, now let's also, so that we can kind of get all of our possible examples, to define 2 points, P being, let's say 3 comma -1, and we'll say that we have point Q being 4. So I'm trying to come up with a ideal example. So that would be going to the right. Let's do 4 comma -2. Okay, so first what we're going to do is we're going to create a new vector from these 2 points, P and Q. Okay, so let's first look at if we were to create a vector P to Q, and we'll label this vector, let's call it vector X. Okay, well, let's kind of sketch this down so we can kind of figure out what's going on here. So we're going to the right in both cases and down in both cases. So we'd have an x coordinate and a y coordinate. So our P is at 3 comma -1, and our Q is at 4 comma -2. Okay, so we are saying that this PQ vector needs to look something like this. So, analytically, based off of our lecture slide notes, we do Q1 minus P1, and we're going to call this Q1 and this Q2. We'll call this P1 and this P2. And then we will do Q2 minus P2. Okay, well, Q1 is 4, P1 is 3, Q2 is -2, and P2 is -1. Okay, so we'll get 1 comma -1. Okay, so this looks good. Now we can kind of realize that that's what this looks like just by sketching it down. We didn't really need to go through the analytical proof. We just needed to know that we were going to the right by 1 and down by 1. Right? And remember, we can translate vectors anywhere. So this is that exact same vector x. Okay, so this is also x. Now, for the sake of what we did in class, or in the lecture notes, we had also said, well, what's the difference when we swap these two? And we expect, remember we expected the direction just to be swapped. So rather than going to the right and down, we expect to go to the left and up. So we should expect this to be -1, 1. But let's just show this. So this ends up being P1 minus Q1 and P2 minus Q2. And so we're going to have 3 minus 4, -1 minus -2. And that in fact does go to -1 and +1. Okay, so we would have just had this vector right here. And this would have been if we swapped it. Okay, and then same thing, if we were to translate this up to standard position, we're now just going left and we are going up. Okay. Alright, so now we have this new vector defined. Now let's do some operations. So let's maybe just change colors. Let's do vector addition. So what if we were to do v plus w? Well, we just simply add component-wise. So we're going to add these two components, and we'll add these two components. Okay, so we'd have 2 plus a -1 and a -3 plus a -1. So we would end up having 1, comma, -4. Okay, now let's prove this graphically. So let's get our v vector drawn and our w vector drawn. So our w vector is going to the left by 1 and down by 1. So this is our w, and our v is going to the right by 2 and down by 3. So that's our v vector. Okay, let's get another graph going on so it doesn't get too messy. But what we can end up doing ultimately is we can say, let's take head to tail. So we're going v, let's move this up a little bit. So we're going to take v, which is going to the right by 2 and down by 3. Let's maybe change the colors slightly on that one. So that would be green. Maybe we should give it a label. And our w, we're going to go now head to tail, so we want to start here and go to the left by 1 and down by 1, so that we end up with this vector right here. Okay, so we've just simply translated that w from standard position so that it's now head to tail with the v vector. Okay, so it's still the exact same vector. Nothing's changed. Then the resulting addition of these two right here is shown graphically. Okay, and that's telling us that we're going to the right by 1 and down by 4 in order to get there, which is what we got as our result right here. Okay, so now I'll leave this, we can do it real quick. So again, this doesn't matter. This is going to be the same thing as w plus v. So if we were to do this differently, we'd say w is now our base vector, so going to the left by 1 and down by 1. And then we want to translate our vector v so that its base is right here. Okay, well, if we start there and we wanted to go to the right by 2 and down by 3, we end up with the same result. Okay, So our addition is still here. Okay. Now, let's talk about scaling. Let's change colors again. Let's take 3 of vector x that we had found, and let's subtract it from vector v. Okay, I'm not going to do this one graphically as well. I mean, it's a good idea to do so. But we're going to take 3 of vector x, which is 1, comma, negative 1, and we're going to add a negative 1, so we're scaling the other vector by negative 1, of v. So 2, comma, negative 3. So now we can scale these by simply multiplying each of the components of the vectors by that scalar component. So we're going to end up with 3, comma, negative 3, plus negative 2, comma, 3, and our ultimate result is going to be 3 plus negative 2 is going to give us a 1, and negative 3 plus 3 gives us a 0. Okay, so we're just 1, 0. And just as a side note, this is in fact our principal unit vector, I, right? So now let's let this go into our next topic, unit vectors. Let's actually, before we go into unit vectors, let's take a step back and let's talk about magnitude and angles of a vector. Okay, so let's say for vector x, in order to find the magnitude of vector x, we have to take the square root of the sum of the squares of its components. Okay, so vector x was negative 1 and 1, so we're going to take the square root of negative 1 squared plus 1 squared. Okay, so the magnitude or the length of this vector just ends up being square root of 2. Okay, now the angle of vector x, and this isn't an exact notation, that's just my way of writing it, to say that that's what we're solving for. We're going to say that this is going to be theta. Missed a component. Tangent of theta is equal to our y component, our vertical component, over our horizontal component. Okay. Now if we were to manipulate this, we know that we can multiply both the top and bottom by square root of 2 over 2. Okay. And we have vector x drawn down here, right? And we can kind of look at this and we can see what we're expecting our angle to be. Well, we kind of expect this to be a pi force angle, right? We just have to make sure that we're in the correct quadrant so that we're pointing in the correct direction. Well, we need to rotate downward. And that's what it actually indicates with this that we had done. But either way, if we solve for theta, we would end up with negative pi force plus 2k pi. Okay. Now, the difference with vectors, and I'll go back to our lecture notes so we can have stuff to refer to. Let's see. If we can find it. Actually, no, it doesn't matter. I was thinking of the angle between two vectors. Okay, so this angle is completely fine, so we can take any of these angles. So let's just take this one. We can take any of the 2k pi angles is what I mean. Okay, so you could have gotten, what would that have been, 7 pi force, which I believe is what a majority of you guys would have solved for the initial base to be. It's just a longer way to rotate to get to the same point. But either way, with this, we can now say our vector x in decomposed form would be the magnitude of vector x times cosine of theta sine of theta, which is going to be square root of 2, and our cosine of theta, cosine of negative pi fourths, is going to be square root of 2 over 2, and sine of negative pi fourths is going to be negative square root of 2 over 2. Okay, and so this would be our decomposed form, and we can double check this just to make sure that we did everything correctly. So let's distribute and scale everything, and let's call this guy vector x hat, because I also want to show you guys something here as well. But either way, if we scale everything, we'd have square root of 2 times square root of 2, which is 2, and 2 over 2 is 1, and then negative square root of 2 times square root of 2 is negative 2 over 2 is going to give us negative 1, which is still our vector x, right? Let's see, yep, right there. Did I mess something up? Something's not quite right. Right, we swapped our components. Oh, I just barely did. I did the green vector x. So we wanted, oh, yep, I meant to do this one. So 1 and negative 1. So let's go through and make some of our adjustments. So we would have said that this would have been 1 and this would have been negative 1. We still would have gotten the same result. And this would have been negative on the top, which is now makes this calculation synonymous, rather than the only reason that I got the correct answer is because I did it graphically just by looking up at the graph of what we expected our angle to be based off of the green one. But either way, now it makes sense. Now it matches, okay? So we were going based off of this green one up here, 1 and negative 1, and we end up getting the same result down here, okay? Now, let's take this a step further, and let's find the magnitude of that decomposed vector not being scaled, okay? So we're only taking the magnitude of this guy. So we're going to have the square root of square root of 2 over 2 squared plus negative square root of 2 over 2 squared, which is going to be the square root of 2 over 4 plus 2 over 4. 2 over 4 plus 2 over 4 is the same thing as 4 over 4. 4 over 4 is the same thing as 1. Square root of 1 is 1. Okay? So what this is telling us is that this guy is a unit vector, which is what we expected. I just wanted to go through the calculation to show you guys how you recognize whether something is a unit vector or not. Okay. Now, let's take it to the next step that I was trying to lead us to, is what if we wanted to create a unit vector? So create a unit vector in direction of W. And I don't remember what W was, so I'm going to go look again. Let's do it in the direction of V. So we have a little bit harder of a calculation. And V was 2 comma negative 3. Okay, so in order to find this unit vector, we need to take vector V, oops, this should have been a regular vector hat, vector V over the magnitude of V, okay? Well, the magnitude of v, we can hurry and solve for over here. We can say that that's going to be the square root of 2 squared, which is 4, plus 3 squared, which is 9. So we get square root of 13. Okay, so now we are just simply, and I'll do the longer way of calculating this so we can show that what we're doing is we're just scaling this vector. So then we're going to distribute through each of these scaling terms to get 2 over square root of 13 and negative 3 over square root of 13. Now, since it's a unit vector, we can check this and make sure that the magnitude is equal to 1. So we can take the square root of 2 over square root of 13 squared plus negative 3 over square root of 13 squared, so that we're going to get square root of 4 over 13 plus 9 over 13, which ends up giving us 13 over 13, which is 1, and square root of 1 is 1. Okay, so we checked that off to show that we did in fact get a unit vector. Okay, now let's talk about dot product. So I want to do 2 of these. We're going to do v dot w, and then we'll also do w dot x. Okay, so first, I guess I don't need to rewrite that down. V dot w. V was 2 comma negative 3, and we're dotting this with, I don't recall what w was, I need to scroll back up, sorry, bear with me, negative 1, negative 1. This is a dot. So what we're going to do is we're just going to take the first components, multiply them together, and then add that to the multiplication of the second components. So we'll get 2 times negative 1 gives us negative 2, plus a negative 3 times negative 1 gives us 3, and we end up with 1. Okay, and this is that key property that you need to make sure that you get is when you take the dot product of 2 vectors, you end up with a scalar value, right? Because this is just some real number. It's a scalar. Okay, and this is an epsilon. It's just saying that that's contained in our real numbers. Okay. And just as a side note, what these guys are contained in, and for those of you that will be going to linear algebra, these guys are still real numbers, but they have a different dimension. So this is saying that this is in the R2 dimension. And this one down here is in the R1 dimension, okay? But either way, that's kind of beyond the scope of this class. So I'm going to ignore that, but just so you guys know when I talk about how this is a scalar, but this is a vector that's composed of 2 scalars, that's how we kind of indicate the difference between the 2. Okay, now we have w dot x, and recall, this is fine for you guys to show on your own. This is the same thing as w dot v. They're synonymous, and same thing goes for w dot x and x dot w. But if we did w dot x, we'd have negative 1, comma negative 1, and we're dotting this with, trying to remember what x was again. X was 1, comma negative 1. Okay, so we're going to have negative 1 times negative 1 plus 1 times negative 1. So we're going to have 1 plus a negative 1, where we get 0. Okay, now it's a scalar value again, but this one is a special case, and we talk about this in the lecture notes. If we have the dot product equaling 0, this means that W and X are orthogonal. This means that their angle is pi halves, or 90 degrees, between the two. Okay? So we can kind of sketch this out again very quickly, because this video's already kind of gone on for a little while. So we have vector W, which is -1, -1, so left and down, and we have the other vector, which is going right and down. Okay? So we can kind of do this brute force. We know that the angle from here to here is pi force, and we know the angle from here to here is pi force. And so we can say, well, what is this resulting angle in here? Well, we know that all three of those angles added together must equal 180 degrees, which is the same thing as pi. And so if we took everything off to the right-hand side to isolate theta, we could say pi minus pi force ends up giving us pi halves. Okay. Now there's another way that we can do this, and we'll do it for the red one as well so we can show. But we can say that we know the geometrical representation of dot product. Okay. So we'd have W dot X is equal to the magnitude of W multiplied by the magnitude of X times cosine of theta. And that theta is what I have drawn in the picture. It's just the geometrical representation. That's the angle between the two vectors. Okay? Give me 1 second. Okay, sorry, I needed to do something on my phone real quick. Okay, so what we can do is we know this is equal to 0. We've already solved for that above. We solved for that right here. We solved for the magnitude of, let's see, where was it? We solved for the magnitude of x right here to be square root of 2. And we also solved for we didn't solve for the magnitude of w, but I know it's square root of 2 because they both have the same length in horizontal and vertical distances, and if that doesn't quite make sense, just kind of go through calculating the length of, or the magnitude of vector w as well. But either way, when we plug everything in, we're going to get 0 is equal to square root of 2 times square root of 2, which is going to be 2 cosine of theta. Then when we're solving for cosine of theta, we'd say that this is equal to 0 over 2, which is the same thing as saying theta is equal to cosine inverse of 0. Well, we know that, and we also know that this angle here, and this is in the lecture notes, so always refer back to lecture notes, the angle between here is always going to be between 0 and pi. So that just means that we're never going to take this larger angle up here. We're always going to take the smallest angle between the two vectors. Okay? But either way, for inverse trigonometry, we know for cosine inverse that this is contained on 0 to pi. Okay? Now cosine is equal to 0 on that interval at pi halves, and only pi halves, okay? So now this is more the analytical way of doing what we just did, okay? Sometimes in this case, we didn't have to do an analytical way. We could have looked at it geometrically like we did. But what if we were doing it for our other scenario? So V dot W. So V dot W is equal to the magnitude of V times the magnitude of W times cosine of theta between those two. Okay, so V dot W was equal to 1 that we had showed above. Okay, I'm going to scroll up again for a second. So we had said that that's what this was. Okay, I'm going to scroll up for a second again because we know the magnitude of W is equal to square root of 2. And I know we found the magnitude of V because we found the unit vector. So let's scroll up and get that real quick. So the magnitude of V is right here, which is square root of 13. Okay. Then we can plug everything in. But before we plug everything in, I just kind of want to give you guys some context of what angle it is that we're looking for. So here's our x coordinate, here's our y coordinate. And W is right here. And V is to the right by 2 and down by 3. So it's down here. Okay. And we know that this length right here is square root of 2. We know that this length right here is square root of 13. Okay. Well, we are looking for this angle between the two. Okay. And again, if the angle is equal to 90 degrees, then our dot product would be 0, but our dot product is not 0, so we know that it is not 90 degrees. Okay. So we have to solve for what that angle is. So let's plug everything in. We have 1 is equal to square root of 13 times square root of 2 is going to be the same thing as square root of 26, okay, times cosine of theta. Then we can say that cosine of theta is equal to 1 over square root of 26. And this means that theta is going to be equal to cosine inverse of, and we can rationalize this if we want to. So we could say square root of 26 over 26. Okay. Now again, cosine inverse is contained on this interval from 0 to pi. And we wanted this angle to be contained on this interval from 0 to pi. Okay, so we don't have to do any manipulation here. This is our final answer for our angle between the two. Okay, we don't have to add pi to it or anything like that like we have in other homeworks. Okay, now let's do one more example that could be related to this. Let's see. Let's take vector v and let's create a new vector. Let's call it y. Okay. We're going to say, what is y that creates a 30-degree angle between the two vectors? Okay. So now we actually know where y is. Okay. We don't know its length or anything. Let's see. Yeah, let's keep on going with this. Okay, but either way, we know where vector v is, so we know that y has to be either going this way or this way. in order to create that 30-degree angle. Okay, so we can solve for two possible candidates of y. Okay, so we can say v dot w is going to be 2 comma negative 3 dotted with, that's what we need to do, because we're missing a piece of information, right? We don't know the dot product and we don't know the length. Let's call this a unit vector of w. I mean unit vector in that in the opposite direction. So we're going to say these are tiny little unit vectors candidates for these y's. Okay, so we can say 2 negative 3 dotted with y1 y2 is equal to, well, the magnitude of v was equal to the square root of 13, and we're saying since this is a unit vector, this means that the magnitude of y is equal to 1, so we're going to say 1, and then we're going to put in cosine. We want the angle to be 30 degrees. Okay? So now, and this can be plus or minus 30 degrees, okay? So we're going to do it for our plus case first. Okay, so this is for, we're looking for like our first candidate of our y vector, okay? So we can say that this is 2y1 minus 3y2 is equal to the square root of 13, and the cosine of 30 degrees is square root of 3 over 2. Okay. Then we can say, okay, we have, let's see, this is definitely a little bit more complicated of an example. We'd have square root of 39 divided by 2. Let's see. You know, we may have created a problem that is not solvable. As we have 2y1 and 3y2. We have a system of equations, two unknowns, but one equation. Let's just continue this on. So we can say vector y2, if we wanted it to be a negative angle, we could say 2, negative 3, dotted with y1, y2, is equal to square root of 13 times 1, and then we'd have cosine of negative 30 degrees. This is going to get us to the exact same result, right? Because cosine of negative 30 degrees is still square root of 3 over 2. You know what? I think this is a little bit beyond this class anyway. I will post a note about this if I notice that there's questions like this on the homework. But for now, just so that we don't keep idling in space here, let's move on so that we can at least get one more example with projections. Okay. So let's go back to our lecture notes so that we can get our formula for projections. So this is projection of vector B onto A. So we're going to copy this over here. So let's paste this down here. Let's give this a new color. Okay. So what this is telling us is that this is our projection of vector B onto vector A. And that is equal to the dot product between the two, A dot B, over our magnitude of b squared if we were to distribute that through in the bottom. And then we're scaling this by we're scaling vector b by this, okay? And that's exactly how this reads, right? And that's what we would expect. We're projecting a onto b, so we're expecting it to be in the same direction of vector b, so we're expecting only to scale that vector b, okay? So let's do this for our, let's do it for v dot w, because we have everything already solved for down there. It's just a matter of figuring this out, figuring out what goes where. So let's project w onto v. Okay, so we want to take the dot product of the two, v dot w, over the magnitude of v squared, and then we want to scale vector w by that. Okay. Well, the dot product of these two was, and again, this is something that we've already solved for, so let's go figure what that was. The dot product of these two was 1. And the magnitude of v, again, this is something that we've already solved for, was square root of 13. And then we're going to square that. Okay? And we're scaling vector w by that. And once again, I do not remember what vector w was. So vector w was -1, -1. So that if we scale this entire thing, what we end up getting is we'll get a -1 over square root of 13 and a -1 over square root of 13. So let's sketch this out. So that, and note, this is actually a good thing to check. This is not equivalent to projection of w onto v. And that would be a good example for you guys to go through on your own. So they're not equivalent, okay? But let's at least sketch this out, what we have going on right now. So we have vector w is down one to the left one. Almost drew that incorrectly. Okay. And then we have vector v, which again, I don't remember what that was. It was 2, -3. So we're going to the right by 2 and down by 3. Okay. So now what this means is the vector that we had just found is going to be, and again, if we were to scale these or convert these over, this would be square root of 13 over 13, negative square root of 13 over 13. Okay, and we're creating an orthogonal projection. So what that means is if we were to look at this vector right here, we're basically casting a shadow onto this vector w, so that it creates this nice orthogonal projection here. And what the result is that we found is that this is that vector that we had just found. Okay? So this is the projection of vector v onto w. Okay? But either way, we've already solved for it analytically. That's just to give you guys some context visually as to what it is that we solved for. But either way, that is it. That's about everything, any kind of example that you can expect to see with vectors. For story problems, refer to the already posted lecture videos from Kelly's lecture videos. If we're still having troubles with those, let me know and I'll consider holding maybe a real-time session and going through a few of the story problem type examples with vectors. But either way, that is it for these examples. I'll see you guys next week.